All right, so we've just got to finish this discussion of tangent planes today, which is really very straightforward, I think, right? Because there's a very simple formula for finding the equation for the tangent plane. There's one other kind of subsidiary topic here, which is finding what's called the normal line to a particular surface at a point. And that is the line that is perpendicular, quote unquote, to the surface. It's not really perpendicular, right? Because the surface may not be a plane, but it's perpendicular. But we say it's perpendicular to the surface at a particular point because it's perpendicular to the tangent plane at that point. So that's the normal line. But remember, the normal vector at the point is going to be perpendicular to the tangent plane, and then you can use that normal vector, right? To you can use that normal vector to find the equation for the normal line, right? Okay, because the normal vector will be the parallel vector for the line. So you can use that vector in writing down the formula for the line. Remember, if you want to write down a formula for a line, right, and you have the vector that's parallel to the line, and easily write down the equations, right, for the line. Remember, you're going to have those parametric or symmetric equations for that line. It's easy to derive from vector that's parallel to the line if you know a point that's on the line. But a point that's on the line will be the point on the surface that you're dealing with. Okay, so all right, that's a mouthful, but that's easier said than done, maybe even. Okay, so this is where we were at last time, just introducing this theorem, right? Okay, which just introducing this theorem, which tells you the equation for a tangent plane, right? At a particular point, right? And point here is x0, y0, c0. That's the point that's the given point on the plane, right? And if you know the partial derivatives evaluated at this point, then you can then it's very easy to write down the equation for the tangent. This is really one of the easiest topics, I think. But of course, you do have to remember this equation, right? And then you can see, right, from the equation from the tangent plane, right, what the normal vector for the tangent plane is going to be, because that's just going to be these coefficients here, right? So the normal vector, or the formula for the normal vector, is given by this equation. Peel off that coefficient of x minus x0. That's going to be the coefficient of I in the normal vector. Coefficient of I minus y0, right? That's going to be the coefficient of j normal vector. And then the coefficient of z minus c 0, right? That's going to be the coefficient of k. But that always turns out to be -1. So that's just always going to be given as -1 for the vector. And then you really don't need to write down the normal vector, right? To write down the equation for the plane, because the normal vector is sort of built into, right, the equation for the plane. And then once you know the normal vector, right, then you can write down either the parametric equations or the symmetric equations for line that's parallel to this vector, right? That goes through your given point, which is x0, y0, and then z0. So that's kind of just automatic. So really, all you need to be able to do here is just take the partial derivative that your home in terms of tangent planes. Okay, that's the last topic that's going to be on the test. So there's that's certainly a formula, right, that you would want to include on your. That's certainly a formula, right, that you may want to include on your a survival card if you can't remember that, but it's pretty easy to remember. Okay. A little bit trickier to remember, right, might be those formulas from the previous notes where we're dealing with differential derivatives, right? And not differential derivatives, but directional derivatives, and then gradients, correct? We have some more formulas coming up today in the new notes where we're talking about extreme values. So I mean, local maximum points or local minimum points on surfaces, but that's not on the test. So you don't have to quite remember those, memorize those quite yet. Okay. Now, but before we get to the notes, so we're going to start with an example here. So I'm going to let you do this example, which is just an application of this this tangent plane formula, right? But before we get to that, let's see. I think we have a homework question. So Amber had a question from the homework that's due today. Oh, I think I moved it back some, but that's okay. It's going to be due soon. So this one on directional derivatives, yeah. So that's one I just mentioned that has maybe a bunch of formulas in it. So I think that problem you ask has so many parts. That's what's so annoying about that problem. It's just goes on and on and on. It's really kind of unnecessarily long. Yeah, most parts of it you did actually. It was just a few things on there for some reason. Which one was that one? So it's this one, right? Okay. All right. So they wanted you to sketch this surface. So this is a plane. So you're going to have to figure out as best you can on how to sketch that. All right. Which one of those is the right one? All right. That's not the crucial part of this problem. What's harder here is some of the other parts where they're asking you to find directional derivatives, and then they're going to ask you to find the gradient, right? Okay. And then ask you other questions that are related to the gradient. Okay. You might try using Wolfram Alpha and see if you can plot that and figure out which one of those is the right. Those graphs are so terrible that it's very difficult to see which one is, have any idea there which one is the right one. I can't even tell what those graphs are purporting to show even. Okay. So I wouldn't ask you something as confusing as that on the test. All right, but let's look at some of these later parts. Okay. If you look at the sample test, I don't think there's not much in the way of graphing on the sample test. Okay, so oh, speaking of the sample test now that's posted, right? That's posted on the Blackboard page. I will work out the solution, so I'll probably post those sometime this weekend. And then before, so I'll send you an email when the sample test solutions are posted. And like before, I will make out a video of just some of the highlight problems, okay, from the sample test. I think most of the problems on the sample test, though, are really straightforward, except maybe the very first problem may throw you, because it's a question about surfaces that are cylinders, and we talked about those, but we didn't really stress those. So I'll try to say in the video as best I can the explanation of that problem. It's not a difficult problem, but it may be confusing because of the terminology and the fact that we didn't really talk about surfaces. We did talk about it, but we didn't talk about it at length and practice it much. Surfaces in 3 dimensions that are called cylinders. Okay, that's just a type of surface in 3 dimensions. All right, so finally now back to this question. So do you remember, Amber, which part? This may look different from your problem, but maybe not. Just part B in general? Okay, all right. So if we do one of those, then part C. Okay, you did part B. All right. Well, let's look at one from part B and just show how to do that, right? Okay. So so it's asking us to find the directional derivative, right? This is a directional derivative, all right, for this surface, which was that plane that had the formula that was written above there. That was a plane, right? That was the that's the equation for a plane. Because if you let fxy be z instead of fxy, then what you really have there is the equation for a plane. All the variables, if you replace z here, all the variables would just be raised to the first power. So that's going to be a plane. That's why they're showing you 3 planes there, or 4 planes in those graphs. All right, so in any event, we want to find then the directional derivative on that surface at that point. 3, 2, where x is 3 and y is 2, so we can calculate the z coordinate if we want to for that particular point, but we don't really have to, I don't think, to answer this question, right? So we want to find what's the slope or what's the derivative. That's what directional derivative means, right? In the direction of this vector. So they're giving us a 2-dimensional vector, right? Because we're thinking of a direction, giving us a direction on the xy plane, right? How do we want to change our xy coordinates, right? So that if we change our xy coordinates in given direction, right? How will that change the z value, right? And what's the slope of that surface in the given direction? And here they're giving us the vector u in this is in unit form, right? So they're telling us cosine. So they have it in the form cosine theta I, right, plus sine theta j. So the theta is the direction, 2-dimensional direction, right, of that vector. And they're just giving us different choices for theta. So really the only thing we have to remember here, right, is the formula for directional derivative. So that's something that you probably want to include on, either memorize or include on your index card. Let me switch over to the notes. So y'all are going to have to help me a little bit remember things. So let's remember that the formula for that function, right? So 3 minus x over 3 minus y over 2. And let's do here, just for fun, part 2, where theta here, the direction for this vector is 2 pi over 3, right? So let me find some blank paper here. Here we go. Okay, so what was that function? fxy was 3 minus x over something minus y over something, right? You remember what those denominators were? X was over 3 and y was over 2, right? And we wanted to find the directional derivative, right? From this particular point. So what was that? 3 comma 2, right? Yeah. Okay. And the particular vector, the particular direction, right, in which we wanted to find the slope, right, is in this direction. So that was cosine of 2 pi over 3, right, times I plus sine of 2 pi over 3 times j. Okay, because they wanted to go in the direction of 2 pi over 3, right? Okay, so let's see, what is this? So we just have to remember, what is this formula for directional derivative? Isn't it the first partial with respect to x, right? Evaluated at your given point, correct? Times the cosine of the direction, right? Which is 2 pi over 3. And then plus the partial derivative with respect to y evaluated at your given point, right? Times the sine of the direction, which is, again, 2 pi over 3. Is that all it is? So I do have to be able to compute the partial derivatives, right, and evaluate them. And I have to figure out what sine and cosine of 2 pi over 3 is. I think I can remember that. But other than that, it's just a matter of filling it in here. And notice you're going to come out with a number, right? Because this is a slope, this is a derivative. So you're not coming out with not going to come out with a vector as an answer here. But later on, we'd be asked to compute the gradient. That will be a vector, right? Okay, so let's see, what are those partial derivatives in general here? So the partial with respect to x, that looks pretty easy. Isn't that minus 1/3? Because this is a constant, so its derivative is 0. The derivative of this term, well, this is just x to the first power, so the derivative of this term is just the coefficient, which is minus 1/3, and this also is a constant, right, with respect to x. So you just get minus 1/3, and what's the derivative there? Y, and that is minus 1/2 for really the same reasons, correct? Okay. So notice our partial derivatives are constants, right? Our partial derivatives are constants. So on that plane, when you're moving parallel to the x-axis, that's the slope of the plane parallel to the x-axis. It's always minus 1/3. Notice that's a constant. Because why is that? See, you have a plane, right? Okay, the surface is a plane. It doesn't have any curvature in it. The surface is just a flat plane. But remember, this a partial derivative with respect to x, right? You find that by slicing through your surface, right, with a vertical plane that's parallel to the x-axis. So when you slice through your plane with a vertical plane, right, okay, what sort of curve are you going to get when you slice a vertical plane with just a plane? What sort of curve do you get? A line, right, okay? And lines have a constant slope, right? So that's why your first partial derivative is a constant here, right? Same thing for your first partial with respect to x, your first partial derivative with respect to y, same reason, okay? You'll slice through your plane with a vertical plane that's parallel to the y-axis. Well, when you slice through this plane with a vertical plane, again, you just get a straight line, right? Okay, and it has constant slope. So that's why the first partial with respect to y is constant. All right, well, okay, that's all just an observation. Let's fill these values in, right? So now you get minus 1/3, right, times what's the cosine of 2 pi over 3? Is that is that the hard part here? Trying to remember what the cosine of 2 pi over 3 is. Is it minus 1/2? Okay, I'll buy that. All right, and then plus here the minus 1/2, right? This partial derivative times the sine of 2 pi over 3. That must be square root of 3 over 2, right? So you just have to add these two. Fractions together. Wow, that's easier said than done, right? This is positive 1/6 minus something, right? Square root of 3 over 4. Did I make you combine those in the answer? Oh, you can leave it like this? Oh, thank God, right? Okay, but we could do this. This is 1/6 is 4 over. Well, I don't have to use. I was going to use 24 as a common denominator, right? But I can use 12. This is isn't this 2/12 is 1/6, right? And this is 3 times the square root of 3 over 12, multiply top and bottom by 3, right? And so you end up with 2 minus 3 square roots of 3 over 12. So just want to write it as a single fraction. There it is. Okay. All right. So those are pretty straightforward, right? Because of the way the formula for directional derivative is written, right? It involves the sine and cosine of the direction, right? And the direction of the direction vector, but they gave us here explicitly the direction of the direction vector. So there's really no work to do there. But now is okay. So now, as Amber pointed out, so what happens when they give us the direction vector, but they don't tell us what its direction is? Then we have to figure it out ourselves. Okay, but that's not hard. So if you're given a vector, right? Okay, if you're given a vector, right? Remember, you can determine its direction, right, by normalizing the vector, that is, making it into a unit vector. So that's what they're suggesting here, right? We're going to give you a vector. We want the directional directional derivative in the direction of this vector, but you need to turn that into a unit vector, right, to really do these calculations. So that's what you have to do first. Did you miss the last one? Okay, all right. So let's try this one, since that's the one that was causing you problems. So v is the vector from 3, 2 to 4, 5. Okay, so notice they're kind of making this visually clear to us, right? Because we're starting at the point 3, 2, right? And we want to know what's the slope in the direction from that point to this point. Okay, so if we're going from the point 3, 2 over to the point 4, 5, what's the slope of the surface in that particular direction? All right, so let's do the calculations here. All right, so we still need this information, correct? But now, before we start calculating the directional derivative, we need to change that. Well, first, let's see what that vector v is, right? And then we need to put it into unit form. So what is that vector v? Let's see, it went from 3, 2 to 4, 5, right? So the I component is what, 4 minus 3, right? And the j component is 5 minus 2. Don't let me make a mistake there, so y'all can remember those coordinates. So this is what, I plus 3j. And now we need to put that in unit form, right? So they're calling that the vector u. So that's going to be v divided by its magnitude. So we need to calculate what the magnitude of v is, but that should be really easy, right? Because that's just the square root of the squares of these coefficients. So isn't that 1 squared plus 3 squared? And so that's better known as the square root of 10, right? Okay. So we would have 1 over the square root of 10 times I plus 3 over square root of 10 times j. Now, why is it so convenient to have it in unit form? Well, I think kind of this formula kind of requires that, right? But when you put it in unit form, it makes the rest of the problem really easier, right? Because what do you know? You know the cosine of the direction angle is what? It's just this coefficient, correct? So that is going to be 1 over the square root of 10. So you really, Amber, you don't really have to know what theta is. I don't know the angle whose cosine is 1 over the square root of 10. I really don't care what theta is, because I know it's cosine. And cosine is really all that I. So can skip that ugly step of trying to use the inverse cosine, right? And then what's sine of theta going to be? Just this coefficient, right? So sine of theta, pretend that's a theta, is 3 over the square root of 10. And now we're in business, right? All we have to do is just plug numbers into our directional derivative formula. So the slope of this surface at this point in this direction, ooh, there's a lot going on in that notation, right? Okay, so the slope of this surface at when x is 3 and y is 2, right? In the direction of this vector u, is going to be, well, that first partial derivative again, which is a constant. So that's minus 1/3 times the cosine of your direction, right? But we know that is 1 over square root of 10. And then what? And then this partial derivative with respect to y, which was what? Minus 1/2. And then times the sine of the direction, which is 3 over 3 over square root of 10. So this looks like what? Minus 1 over 3 square roots of 10, minus 3 over 2 square roots of 10. Oh my word. Okay. And now I don't want to add those two. Now I don't want to add those two fractions together. Well, but let's not be lazy. So what common denominator can we use here? 6 times the square root of 10 as a common denominator. So multiply top and bottom here by 2 of the first fraction. So that would be minus 2 over 6 square root of 10. And then multiply top and bottom here by 2. So we would have 6, I'm sorry, multiply top and bottom here by 3. So we would have 9 over 6 times the square root of 10. And so that looks like minus 11 over 6 times the square root of 10. Hardly seems possible, but we'll have to trust the mathematics here, right? Okay. So hope I didn't make a error there. It's y'all's duty to warn me if I've done that. Okay, now the rest of these problems now they want us to sort of dealing with the gradient, right? Okay, so the gradient tells us in which direction we want to move, right, to get the maximum slope. Okay, right? So this 0.32, right, where we probably move to go up that plane, right, as quickly as possible. It's not going to be in the direction of the x-axis. That slope negative, and not going to the direction of the y-axis either. That slope is also negative, right? So, but we want to go up, so surely we can find some direction, right, where we can move up that plane, right? Let's see what it is there. Okay, so that's what the gradient will. That's what the gradient will tell. So what's the? Now I've forgotten now, right? So what is the formula for the? What's the formula for the gradient? Oh, okay. So partial derivative with respect to x, right? You just multiply that by I, right? Plus partial derivative with respect to y, right? Times j. Yeah, I think that's it, right? Okay. So let's see. Well, we can just fill those in, correct? Because we know what these partials are. So it's what? Minus 1/2 I, right? Minus 1/3 times, or did I get that backwards? Okay, so minus 1/3 times I, right? Minus 1/2 times j. Okay, so apparently that's the direction to move in, right? To ascend that to ascend that plane, right? The fastest. Okay, that's the direction of maximum ascent. Now, I'm not convinced here now, but so let's actually compute what that maximum ascent rate is, right? So what is the slope in this direction? So if we really do go in this direction, how fast are we moving up that? How fast are we moving up that plane? By the way, since this is a plane, we're moving up, right? Again, the slope in this direction is going to be constant. So if you keep going in this direction, you're going to be going up the plane always at the same rate. You know, that won't happen on other surfaces, right? Where you might have hills and valleys in the surface. But since this surface is a plane, right? If you move in this direction, whatever slope you're going, whatever slope you're going at, right? Whatever rate you're going at in this direction, if you keep going in this direction, you're going to keep going up at that same slope. Okay, so what is that now? So this is what we got confused about the time before last, but we fixed it last time. This is easy to compute. What's the formula for this? It's just the magnitude of the gradient, right? Yeah. So I remember last Wednesday we did this. We calculated the slope and the direction of the gradient. We went through a long big process, right? Because we used this formula, the directional derivative formula, to do that, and it took us a few minutes, right, to do the calculation. And then we realized afterwards, oh, that was probably unnecessary. Indeed it was, right? It just turns out to be the magnitude of the gradient. So that's one of the nice results from calculus 3. So we just take the minus 1/3 squared, right? And the minus 1/2 squared. And then take the square root of that sum, right? So this is 1/9 plus 1/4. Take the square root of that. What is 1/9 plus 1/4? You should be able to do that. What common denominator can we use there? 36? Yeah, so this is 1/9 is 4/36, correct? And 1/4 is 9/36. So you just get the square root of 13 over 36. And you can then, break that up as the square root of the numerator and denominator. And that's useful in this case because the denominator is a perfect square. The square root of 36 is 6. So you end up with not a bad value there, square root of 13 over 36. So indeed, if you move in this direction, right, you are going to be going up the plane, okay, at this rate. It's not a very big rate, right? That's less than 1, but a little bit more than 1/2 though. So maybe not that bad. Okay. All right. So now, does that make sense? All right. Now, the next problem is a little bit confusing. Can y'all make so this is E, all right? But this is the part that was a little bit strange, all right? So it says find a unit vector that's orthogonal to the gradient. Okay. So let's see if we can find a vector. We can always put it in, we can always make it a unit vector, right, by dividing by its magnitude. But can we find a vector that's orthogonal, in other words, perpendicular? This seems perpendicular to gradient vector. Orthogonal is another term that's often used. Because orthogonal actually applies to an angle. Orthogonal angle is an angle. So that's why. All right. Any suggestions on how to go about that? All right. So help me with that. They're orthogonal if their dot product is 0. Okay. So how does that help me, Robert? Oh, you have to get it 0. All right. So did they give a name for this? Did they give a name for this vector that we're looking for? U? Okay. So you're telling me that if I take this hypothetical vector U and I take the dot product of that with the gradient, right? That's the name for the gradient. Then I'm supposed to be 0, right? Okay, so that's the clues that we're going to use. All right. So let's put this in not in standard form, not in IJ form, but let's write these vectors in this is called component form, right? So let's call this we need variables names here. So let's call this vector u AB, right? Okay. And then dot the gradient vector. What's the gradient vector though? Minus 1/3 and minus 1/2. So when you take that dot product, you've got to get 0. So let's write down these, let's write down what this is going to be. So we have minus 1/3 times A minus 1/2 times B, right? Has to be equal to 0. So any suggestions for A and B that will make that true? Can you solve that by inspection? How about what if this one is 6? So if A is 6, you would have minus 1/3 times 6, right? And then what can you get? That's going to be minus 2, correct? Negative 4? Oh, so B would be minus 4. That would work, right? Because here you would have minus 2 and this would be plus 2, would give you 0. Oh, okay. So yay, so that does work, right? If we think about it a little bit. So this looks like 6i minus 4j. Oh, nice. Okay. So that must be orthogonal to the unit vector because the dot product is 0 if we did these calculations correct, right? And then we just put that into just normalize that, right? Put that into unit form. So take this and divide it by its magnitude. Okay. So I'll skip that part, because y'all can do that easily. So Robert, that's a clever suggestion. That makes it kind of easy. There are other ways you could think about this also to find a vector that would be orthogonal, perpendicular to the gradient vector. That's nice though because this is nice because it uses the dot product. What was the last question though? So something strange is going to happen here. Okay. All right. It's not clear why this is correct. All right. So the gradient, what is the direction of, what is that? Greatest rate of change, right? From F, correct? So in a direction orthogonal to the gradient, the rate of change is going to be, any suggestions? Not opposite, right? If you go opposite to the gradient, if the gradient is the direction of greatest slope, then opposite of the gradient would be negative of the gradient would be smallest slope, right? Okay, right? But this is orthogonal. Yeah, and so it's not clear why they expected to know this. It turns out to be 0. So orthogonal to the gradient, the rate of change will be 0. So I just tell you that answer. I didn't know. I saw that question. I wasn't sure why they expected you to how they expected you to figure that out. Okay. Maybe we could deduce that, but yeah, we could probably deduce that with a little bit of work, but it's not clear. We could probably prove that with a little bit of work, but it's not clear why they expect you to just immediately understand that's the case, okay, without thinking about it more carefully. All right. Okay, so so that was Amber's question. Are there other questions from that you have so far from this question? So remember, this last question is going to be like that example, right? That lengthy example that we did in class about the spaceship, right? And the heat on the surface of the spaceship. So you can use that example from class to maybe help you with problem number 11. Okay, but that's not really as hard of a question as the example that we gave in class, for sure. Okay. Remember one other thing, right? How do you find a perpendicular vector to a level curve? So if you have a surface, you remember you create a level curve. That's a two-dimensional curve, right? By setting your formula equal to a constant. So that gives you a curve that you can graph on the XY plane. And how do you find a vector which is perpendicular to that level curve? That's the same as what? That is the gradient vector. So the gradient vector is perpendicular to a level curve. Okay. All right. Okay, so let's switch back to the notes, and all right, so we're going to use this formula. So you may want to jot that down quickly. I'm going to show you the problem, but we won't be able to focus on the screen simultaneously, right? Okay, so there's the formula for the tangent plane of a surface at a particular point, right? So again, this is point x0, y0, z0. That coordinates, the three coordinates, right, for your point on the surface, and then the partial, right, evaluate x, y coordinates. That point. Just plug those into this equation, and just plug those values into this equation, right? And you get the equation for the tangent plane. So I'm going to have y'all try one here, right? So find the equation for the tangent plane of this surface, which is, I got this weird equation, x times y times z is 12, at the point 2 minus 2 minus 3. So I think that point, 2 minus 2 minus 3, is on that surface. That correct? So if x is 2 and y is minus 2 and z is minus 3, yeah, multiply those together, you'll get 12, right? So this point is on that surface because it satisfies that equation. So here's a picture of that. Here's a picture of that surface. So notice it's got a bunch of separate pieces to it. They're all separated. Looking tangent plane, this point, not right there. This picture. Right. And then also we want to write down what's the normal vector to the tangent plane. So what's the vector that's perpendicular to tangent plane at this particular? So this is the normal vector is a three-dimensional vector, right? This isn't a gradient vector. This is a three-dimensional vector, so it's going to have a K and a K, right? Let me show you now. However, this equation, you want to, before you start here, we need an equation with two variables. So take that equation and solve it for z. Take this equation and solve it for z. So you would have z equals 12 over x times y, right? Divide both sides by x times y. So and z, remember, is the same as fxy. So there's your function of two variables. It's just 12 over x times y. Okay. So before you start using any of these formulas, right, you have to you have to write your equation in the proper form. You need it as a function of you need z as a function of x and y. Okay, all right. So can y'all do that? Just so you get a couple of partial derivatives to compute, and then do some evaluation, right? Then just plug it into that formula, right? So it's really easy to write down the tangent plane. Can y'all find those partial derivatives? Make sure you do your differentiation properly. So careful. That's right. Good. That's right. The derivative of unknown x. X. Find it. Really well. Differentiate this just not the derivative of 1 over x is not natural log of x, by the way. So yeah, that's the end of it. So what's the derivative for x? That will help. This is one of this. So a so it can be in there, but it's gonna mess up your. Really have to. Um, yeah. Then so y'all making good progress. Y'all figure, y'all did figure out the. Y'all did figure out. Ever figure it out? Oh, oh, are you? What are you telling me? That's like that's where. Ah, yeah. Text me. So yeah, y'all have forgotten your favorite differentiation rule, which is the power rule. People often forget to apply that to negative exponents. It works just as well with negative exponents as it does with positive, and with fractions too. It's very powerful. Okay, I'm going to start. So most of y'all have, or a lot of y'all have gotten well into this. You're not completely through. That's fine, right? Okay, so what I was suggesting to people as I was walking around, right, is you can think of this formula in lots of ways that will be helpful when you're trying to compute the partial derivatives. You can think of this as 12 over y times x to the minus 1 power, right? Okay, because x to the minus 1 power is 1 over x. So 12 over y times x to the minus 1 is the same as this formula, or vice versa. You can think of this as 12 over x times y to the minus 1, and that makes it easier when you're trying to compute the partial derivative with respect to y. So what is the partial with respect to x? Well, let's see. Let's use this version of our formula. So we just apply the power rule, right? Bring the minus down, correct? So bring the minus 1 down. So you would have minus 12 over y, and then subtract 1 from the exponent. So that would give you x to the minus 2 power, right? Subtract 1 from the exponent. We're differentiating, not integrating. And then when you just clean this up a little bit, this is the same as minus 12 over y times 1 over x squared. X to the minus 2 means 1 over x squared, right? So you get minus 12 over, if I write the variables in alphabetical order, I would have minus 12 over x squared y, okay? And then you can easily see, right, just by symmetry, because these two formulas are very similar, right? Except here you have x to the minus 1, here you have y to the minus 1. So you can see easily, right, that when you compute the partial derivative with respect to y, you're going to get almost this same formula, right? Instead of having x squared, though, you'll have y squared, right? So the partial derivative with respect to y turns out to be minus 12 over xy squared instead of minus 12 over x squared y, right? And now let's see, what do we need to do with those partial derivatives? Well, we need to evaluate them at this point, correct? So I need to compute the partial derivative with respect to x at the coordinates, the xy coordinates 2 minus 2, right? So I'm going to plug 2 in for x and 2 in for y, and minus 2 in for y, I'm sorry, right? And what does that come out to be? 3/2? Um, so I'm doing that in my head, but it's y'all can do that on paper. I think this is 2. In fact, this is 2/2. And then what does the y? What happens to the y? It's going to be almost the same, right? But is it negative 3/2 or something? Is that right? Ah, okay. And now we're just in business, right? From this point on, it's so easy because the formula for the tangent plane, right, is going to be this partial derivative times x minus the x coordinate of your point, right? So times x minus 2 plus this partial derivative, right? The partial derivative with respect to y times y minus the y coordinate of your given point, right? So that will turn out to be y plus 2. When you subtract a minus 2 from y, you'll get plus 2 there, right? And then remember, is it always minus here? 1, right? Times z minus the z coordinate of your point, right? So this coefficient is always fixed at -1, and then all of this is equal to 0. So there is the equation for the tangent plane. So apparently if we were to graph that, darn it, I should have thought to make a graph. Graph the tangent plane and this surface simultaneously, right? That tangent plane should just touch this surface, right? Not supposed to slice through the surface, right? Close to this point. Tangent plane is really supposed to sort of be parallel, right, to the surface. at this point. And here's the normal vector, right? That's so easy to write down because the normal vector for your surface is the same as the normal vector for the tangent plane, right? So and you can read that right off formula for the and read that right off the formula for the plane. So that's so that normal vector is going to be 3/2 I, right, minus 3/2 j, and then minus k. You always end up with minus k in these normal vector tangent. Now, how can you turn that into the formula for a line? So suppose you didn't want this vector, but you wanted to know what's the formula for the line that is so the full line that's perpendicular to this surface right here. Okay, so how do we write down the it's got to be equations, right, for this line now in dimensions. Let's write down the parametric equations for this line in 3 dimensions. But this vector now, it's the normal vector for the plane, but it's going to be the parallel vector, right, for the line, correct? And so how do you write down equations for lines when you know vector that's parallel to a vector that's parallel to the line? Isn't that easy? In parametric form, remember you get x equals y equals z equals, right? And how do you fill in these equations? Remember that from test number 1? So you start off with what? A point that's coordinates for a point that's on the line. So here you would have what? 2, -2, and -3, correct? And then what's the second term in each one of these equations? Just what? Yeah, that's right. The coefficients of n, right, times t, right? So you would take this first coefficient, 3/2, right, times t, and then this second coefficient, minus 3/2 times t, right, and then this third coefficient, which is always -1, right, times t. Oh, so that's so easy, right? So there are the parametric equations right, for this that line that I have. Well, I have another example here, but I don't think we even need to do it. But let's do it quickly because it doesn't look wow, I don't know. Maybe it does look bad. So we want to find what are the parametric equations for the normal line. So that's the normal vector but turned into a line, right? So the normal line, the line perpendicular to this hyperboloid, this is a hyperboloid. And it apparently goes to the point -2, 2, 3. Do I believe that? Yeah, maybe. Okay. Right. This says equal 1. I was thinking that equal 0. That's equal. So if you plug these coordinates into this equation, they will satisfy the equation. So this hyperboloid does contain this point. Let's see what that hyperboloid looks like. So the top half of the hyperboloid at least looks like this, okay? And we're really interested in the top half of the hyperboloid, right? Because that's where the point -2, 2, and 3 is, right? So everything on that this hyperboloid will have a bottom piece as well. Okay, which is not shown there in the picture. So if you take this part and invert it, move it below the z-axis, same distance. This is above the z-axis. I think this hyperbola has a second part not shown. All right. So how would we do this? What would be the first step here? I have some suggestions there. See, I have this equation in the variables x, y, and z, right? But I need a function of two variables for all of my groups to work. I need an fxy function. So I got to turn that equation into a function. So how do I do that? Solve for z, right? So you have to solve that equation for z. Easier said than done, but you can first, right, move some terms around. So you'll have z squared is equal to 1 plus x squared plus y squared, right? And then you want to solve for z. So how are we going to solve for z there? Take the square root of both sides, right? So you'll get z, that's going to be your fxy, right? Would be the square root of this. But you know, numbers have two square roots, right? They only have one cube root. That's going to come up later today. But they have two square roots, so we have to think about both square roots. But I have to have a function. So this is not a function, because if you plug in values for x and y, right, you get two possible values for z. So z is not a function of x and y in this equation. So I have to make a choice. I've either got to choose plus square root or minus the square root, because I need a function of two variables. Well, which one is it going to be? It's going to be the positive one, right? Because I only care about what? Really? For solving this problem, I only care about what? The top portion, right, of that hyperboloid. So we can really just sort of ignore the bottom part of the hyperboloid, right, for the purposes of doing the problem. So just erase the negative there, and there's our function of two variables, right? Now that's still a formidable function of two variables, because we have to compute partial derivatives. Yuck. All right. And so that looks like an ugly partial derivative to compute. My suggestion is don't use the square root here, right? Because when you're computing derivatives, square roots are not your friend, right? So what can we do with the square root? Yeah, that's right. Convert that to a fractional power, right? And so that's 1/2 power square root. And that works beautifully, because the power rule for derivatives works just as well with fractions as it does. So it's Newton. So that's great. Okay. So maybe we'll be able to calculate those partial derivatives. Let's see, what are they? So they're going to be very similar to each other, right? Because this equation is very symmetric. What's the it's very symmetric in those variables x and y, right? So what is the partial derivative with respect to x? How's this going to work here? So what do I do? Do I bring the 1/2 down? Is that right? Yeah, that's the power rule, right? So you bring the 1/2 down, and just have to subtract a 1 from that. So when you subtract 1 from 1/2, you get minus 1/2. Okay, well, that's all right. And then, but what else do I need? Yeah, that's right. The chain rule comes into play, right? Because this is not just x to a power. This is an expression raised to a power. So I have to multiply in the derivative inside the parentheses. So don't forget the chain rule. But we're taking the derivative with respect to x. So that's real easy, right? Because the derivative of 1 is 0 with respect to x, and the derivative of y squared is also 0 with respect to x. So you just get 2x here, right? the derivative of x squared. Oh, that works out nicely because the 2 and the 1/2 will cancel. So that's just perfect. And we end up with x times all of this mess to the 1/2 power, minus 1/2 power. But that means you're going to invert this, right? And write it again as a square root. So I have 1 plus x squared plus, can y'all see how, can I squeeze that in there tiny? Plus y squared, that's really bad. So let me erase that and try writing that again. Let's put it down here. So I end up with x over the square root of 1 plus x squared plus y squared. Oh, so it's not so bad after all. Okay. As minus 1/2 power means, well, the minus means you're going to take reciprocal, right? That's how you interpret negative exponents. And the 1/2 means it's a square root. Two's cancel. Well, everything being symmetric, right? Then what is my, since everything is symmetric with respect to y, right? Then what's my partial derivative with respect to, wasn't it just the same thing? Except just switch the variables? So when you take the partial with respect to y, you're just going to get this. And now what do I have to do with those? Evaluate them, right? Okay. So I need to evaluate them at 2 and what is it? What's my point? Negative 2 and 2. So when you plug negative 2 in for x and 2 in for y, let's see what happens there. I think I'll do the top. So that's positive 2. What's the bottom? It's also easy, right? What's the square root of 9? Yay. Okay. So someone must have planned that very nicely. So we just get 2/3. Wow, great. Okay. And what's the partial with respect to y going to be? Negative 2/3, I think. Yeah, but didn't I have, you're right. I was thinking too many negative signs there. All right, so negative 2/3, and then this is positive 2/3. Okay. So great. So so the partials are easy to compute and easy to evaluate. So that's nice. And now we just write down our normal vector. Also easy, right? So that's going to be minus 2/3 I plus 2/3 j. And what's the last component always? Minus k. All right. So there's our normal vector. And then what's the equation for that line? Or what are the parametric equations for that perpendicular line that we see right there? So x is going to be what? Minus 2/3 t, right? And y is going to be positive 2 plus, I forgot the j here, positive 2 plus 2/3 t, correct? And then z is, what was the z coordinate there? 3 or something? Yeah, 3 minus t. Those look like the parametric equations for those lines. Who knows, right? Okay, so it's very difficult to, I know that line goes through that point. Okay, so I'm convinced of that. But is if I can generate more points on that line through that through those parametric equations, we'll just have to trust our arithmetic. Okay, I can make a graph. This is the graph of that line. All right. Now, you know what's coming next, right? Now that we know about tangent planes, okay, remember after you think back to Calculus 1, because all of this is very analogous to Calculus 1. So once you learn about tangent lines in Calculus 1, very next step you're interested in as well, you go through a bunch of differentiation. Okay, well, we don't have that, right? But once you've learned a bunch of differentiation rules, so the next step in Calculus 1 is want to weaponize the tangent. And the way you do that is I look extreme values on it. So by extreme values, I local maxima and local. So where the curve has even, out. Okay. And why is the tangent line so perfect for that? Yes, because the tangent line is going to be horizontal, right? Where you have a peak or valley and a curve, right? Well, going to do just exactly the same thing, except for surfaces. We are going to look for peak and valley on surfaces, right? Okay. But that is obviously going to correspond to what? Where the tangent plane is. Those peak or valley points will be maximum or minimum. It's local maxima or local minimum. But what's going to happen to the tangent plane at a peak or a valley? Tangent plane is going to end up being what? See right here? Right? Tangent plane is going to be flat, right? It's going to be parallel to the xy point. So, tangent planes that are flat, okay, horizontal tangent, okay? That will slope out, okay, just like horizontal tangent lines help you find, right? So the whole process is finding local maxima or local minima, peak or valley points on surfaces is all very analogous to what you do in Calculus 1, okay? Except we'll be using partial derivatives instead of, just a plain derivative, right? So what I just said there is what is essentially what the note said, okay? So definitions in terms about maxima and minima, that means peak points on surfaces, valley points on surfaces are very similar for functions of two variables as they are for functions of. So you're going to find this, I think, pretty straightforward. Now, let me tell you, these peaks and valleys have to exist, okay, in certain situations, all right? So if you have a function of two variables, so that's going to give you a surface, right? If your domain is a closed region, in the xy plane, so by closed region, I mean it's a region that contains the boundary of the region. Right, so if it's a region that contains its boundary, then you're guaranteed that that function will have maximum minimum. Okay, that's called the extreme value theorem. Right. So here's a picture of that situation. So again, if you have a function of two variables that generates a surface, right? If your domain is a closed region in the xy plane, so a region that contains the boundary, doesn't have to be a rectangle. Okay, be any shaped region in the xy plane, as long as it contains its boundary as part of the region, then guaranteed you'll have a maximum minimum of your function. The problem is the maximum or the minimum may occur on the boundary. Right? It doesn't have to occur somewhere in the middle of the region. So the maximum may occur on the boundary. So oftentimes you will have these local maximum or these local minimum on a surface. Right? By the way, there's an example of minimum surface. happens to it. Notice the maximum somewhere. Somewhere. Now, when I say maximum, I mean that's a point that's at least as high as any of the points close to it, right? Any of the points around. Minimum means that's a point that's at least as no, that's a point that is say at least as low. That sounds good. None of the points close to it are lower. That. Technically now, say maximum, if you're referring to the z coordinate, say minimum, always refer to the z coordinate. But usually we're not that careful. And so we often by itself as being maximum. So yeah, this picture shows you that this surface has it's called, as David mentioned, an absolute maximum. So this point is higher than the other points on the surface, right? And this is an absolute. This point is lower than any other surface. But oftentimes we will be satisfied not to find absolute maximums or minimums. We'll be satisfied in finding what are called relative maximums or relative. So these are points that are peak or valley points on the surface. Surfaces, of course, can have lots of peaks in. So surface, right? So peak. But there's some valley to surface. Okay. A relative maximum or relative minimum does not have to be the highest point on the entire surface. Okay. Or a relative minimum doesn't have to be the lowest point on our surface. It just means it's the highest point or the lowest point in a particular. So any peak point on a surface is called a relative maximum. Any valley point on the surface is called if it was the highest point anywhere on the surface, that would be called the absolute maximum. If it were the lowest point anywhere on the surface, that absolute. Now, what I just mentioned in the previous notes, though, is the key observation here. Okay, all right. Going to have a relative minimum, relative maximum, that is peak or a valley where tangent planes are horizontal. As you see, if you have a minimum on a surface, right, that's a low point, that's a valley point surface, tangent point. Or if you have a peak point surface, the tangent plane is going to be horizontal. So the secret to looking for peak points and valley points is to find where the tangent is. That's all. Okay. How's it different from mean value theorem? No, mean value theorem is something. Everything's connected. Those things deal with two slightly. They're partial. So all of these notes, I mean, at some point going to you can read. Summary is okay. Look for valley points on a surface, to look peak points on a surface. Gotta find their tangent. That's the and places where tangent planes are horizontal, those are called critical surface. The definition I skipped over just a moment ago is exactly that definition. Okay, a critical point for a function of two variables is a place where where both your first derivative and your second derivative zero. Okay, or notice there's one other possibility where either first derivative or second derivative is not defined. Okay? Watch out for this one. This is easy to. Okay? So we're going to have a peak or valley points at critical points, right? This is where the first and the second, the first partial derivative with respect to x and first partial with respect to y are both zero, okay? Or where one of these derivatives does not exist. That will happen sometimes. Now, why does this correspond to why does that first condition correspond to having a tangent plane that's horizontal? Well, think about it. How do you find the equation for the tangent plane? What do? You take the partial derivative with respect to x, right? And you multiply it by x minus x0, right? X0 is a point on the surface. You take the partial derivative with respect to y, you multiply that by y minus y0, right? Y0 is the y coordinate surface. Then what minus z0 always is the third term, right? And well, look, if these are both zero, think about what the if those partial derivatives are both zero, think about what your tangent plane is going to look like. The equation for the tangent plane is going to have 0 times this, right? So that becomes 0. It's 0 times this, so this becomes 0. And then you just get the minus 1 times z minus z0. Or if you solve that equation, it's z equals z0. So what sort of surface is that? That just tells you what? It's flat, right? It means the z is always a constant. X and y can be. So you just get a flat plane at this level, whatever this is equal. So comparative structure. An absolute minimum or absolute maximum, that's not easy. Right? Now, look, here's the other tricky part. We'll have, anytime you have a core value, like that will happen only at critical points. So you know that either both the first partial derivative is 0 or one of the partial derivatives is not defined. Careful, it's possible. But so if you have a peak or a valley, one of those conditions has to be true. One or two. But unfortunately, the opposite numbers is not the case. They have one of these conditions being true and not end up with a maximum. I'm going to show you. So be careful of that, right? Let me repeat. If you do have a peak or a valley point, local maximum or local minimum, one of these conditions has to be true. Okay, but but you don't know if one of these conditions is true, have to, and still not have equal. Now, why? Maybe wondering why about this condition? This one's kind of, we explain why this one is true, right? If the partial derivatives are 0, then the tangent plane is going to end up being flat. So clear that's going to be a valley point, right? Or it could be a peak or a. This condition is a little bit less obvious. Back to see examples. Let me try one example here before we before we quit. Okay. All right. So we're going to jump right into it. Find the relative extrema. So that means relative maximum, relative minimum of this function. Okay. I'm not going to show you the graph of this yet, but I do have a graph thing. I'm not going to show you the graph of this one. This is a quadratic surface, though. This is a quadratic surface. So this is some sort of quadratic surface. Okay. So so how would we proceed? How would we start looking for those peak points or those value points? Well, all we have is that condition that I just stated, right? Okay. Only going to have peak or valley points at critical points. Critical points are where both of the partial zero or one of the partial not one. So first thing to do is problems. That's the start of the problem. So let's calculate those. And these are easy to calculate, right? So this won't be hard for us. So what's the partial derivative with respect to x? You would get what? 4x. This becomes 0, right? Plus 8, right? This becomes 0 and this becomes 0. Oh, so that's so easy. And what's the partial derivative with respect to y? That's also easy, right? Isn't that going to be 2y minus 6? Yeah, okay. Oh, so we have these very simple partial derivatives. How nice, all right? And we're looking for where both of those are what? 0 or undefined. Unfortunately, for x plus 8, that very simple formula, that domain is all x values, okay? Because that's just a very simple form, right? And 2y minus 6, the domain for that function is all y values because that's just a very simple formula. So we don't have to worry about the partial derivatives being undefined, but we do want them to be 0. That's our only other option. So let's set them to 0, and oh, it's so easy to figure out, right? What's x have to be here in this equation? Is that minus 2? And here y would have to be what? 3? So it looks like we only got one candidate here, right? X is minus 2 and x is minus 2 and y is 3. What's the z in that case? Yeah, just plug those in, right? Can y'all do those for me? So we have a critical point at minus 2, 3, and if you plug in minus 2 and 3, what does all this reduce to? Shall we do that? Let's do it. So f of minus 2 and 3 would be 2 times minus 2 squared plus 3 squared plus 8 times a minus 2 minus 6 times 3 plus 20. My goodness, what's all of that? 8 plus, this is 8, right? Plus 9 minus 16 minus 18 plus 20. Is that something like 3? Oh, did we already? Well, so there we have it. There's our potential. Well, it's not a potential. That is a critical point. So that is a potential peak or valley point. And now we have to see if we can out. All right, let's look at the graph first and see, and let's just see what we think, okay? And then I'm going to show you. Actually, you can deduce that this really is it's either a peak or a valley point. Let's see what our candidate is. So here's the surface. Oh, so that looks like what is that thing? A parabola, some sort of paraboloid or hyperboloid or something, right? That's a quadratic surface of some type. All right. So there it is, and sure enough. There's minus 2 and 3 hanging around right at the vertex of that surface right here. That surface. So it certainly does look like not only is that a local, okay, right? You can see that's a valley, so that's a local, and that looks like an absolute limit Because I don't think that surface ever gets anywhere below that point, right? So not only is it a valley point, that's an absolute, that's the lowest point anywhere on that particular surface. But now we can see from the graph, graphs of functions in 3 dimensions are hard to construct, and they're even sometimes harder to look at. This one's easy to look at, but wow, how can we figure that out without having graphs? That's good. That's easier. That's going to be tricky. That's easier said than done. In this case, I think we can figure it out. Let me show you. Let me show you why I think. So let's take this formula and let me show you what I'm going to do here. But see, you probably wouldn't think to do this. So let's see. Let's take the, I'm going to group the x terms together. If I'm remembering how to do this right. And I'm going to group the y terms together like this, okay? Yeah, I'm going to complete the square. So here I'm going to factor out a 2 first from just the x terms. So I have 2 times x squared plus 4x, and then plus the y squared minus the 6y plus the 20. Now I'm going to complete the square. Oh, Robert, so you remembered that. Do you know how to complete the square on x squared plus 4x? So I want to add something into the parentheses so that this will become a perfect square. What number can I add in the, so this factors as a perfect square? Remember how to do that? Take this coefficient and divide by 2 and square it all. Take 4, divide it by 2, and square that. So 4 divided by 2 is 2, squared is 4. So you're going to add 4 in, right? So you get x squared plus 4x plus 4. And now you're guaranteed, when you factor this, you're guaranteed this will factor, but it will also factor as a perfect square. Same thing here. I'm going to try to make these 2 terms into a perfect square. So I do that by grouping them together and then adding something inside the parentheses. Take the minus 6, divide it by 2 and square it. So what would that be? 9? So put a 9 in here. Now look, you don't want to change the formula, so you have to be careful. You added something into the formula, right? Here you added in a 4. That 4 is multiplied by 2. So you added in 8. And here you added in 9. So you have to compensate for that. You can't just add those in. So let's subtract them back out. But I'm going to subtract them back out here. See? Okay. So I really haven't changed the formula, but it looks a lot different. Now, this factors as a perfect square. This is x plus 2 squared. And this factors also as a perfect square. This is y minus 3 squared. And how much is this? 23, something like that? 20 minus 17? Well, look, here's my claim. This is always bigger than or equal to 3. Okay, right? No matter what you plug in for x and y, you're going to get a number bigger than or equal to 3. Why is that? Because when you plug something in for x and y here, right? Even if the quantity inside parentheses comes out to be negative, you square it. So that's going to make it positive. So you'll be adding a positive number to 3. So you're going to come out with a number bigger than 2. So what does that tell you? What's the smallest z you get from this formula? The smallest output formula. 3, right. Never going to get anything less than 3. And you can get 3 if you plug what? Negative 2 in for x and 3 in y, right? These 2 will turn out to be 0, and then you'll get exactly. Oh, so what's the minimum point? It's negative 2 for x or y. See, that's the lowest point at function. Okay? As this quantity never going to get, the z value is never going to get below 3. Oh, is that what we see here? Yeah, sure, right? Okay. There's the lowest point on that surface. It's at z equals 3. and that happens when x is minus 2 and minus 3. Oh, that took some algebraic shenanigans, right? And out. That's not something you're gonna figure out. Okay, so keep that in mind. Did find in this case the absolute minimum. It was pretty easy to locate what the candidate point was, but then trying to convince ourselves that really was the absolute minimum. That was not easy. That was not routine. So we got a little bit of work ahead of us, right? Want to kind of make the process a little this, right? Okay, but anyway, there's our first example. We've run out of time. Okay, it's going to be the same process though. Okay, going forward, right? You're looking to find these minimum, maximum, extreme values. Where either what both of the partials are 0, or say this example, one of the partials is under. Okay. All right. All right. Well, we're definitely out of time. You'll have a lot to think about. So don't forget what your homework is due. I moved it back to Saturday, so don't forget that Saturday. That's an unusual date, due date. Okay. And then tangent planes, not till next week, but that's when our test is. And the test goes through tangent planes. So this is not on the test. Just tangent planes is all it's on the test. Okay. All right. See you guys on Monday. Have a good weekend. Go Astros.
So this we find and on and then
Well,
see whether it's sloping towards, and if it's decreasing, it's increasing.
that's sort of what we're going to do, because at a minimum, you sort of have this cup shape, right?
Yeah.
So what does the curvature look like there? It's concave up, right? Okay. Yeah, and at a peak, right, you have this hill shape, right? And the derivative is concave down. But the problem is, of course, in 3 dimensions, is you've got concavity in lots of different directions. So how do we account for all of those directions? And so we will end up using second partial derivatives to do this, but it's going to be a little bit more complicated test than for calculus 1. But the idea is the same, but the formulas turn out to be more complicated. That's all. Okay.
Thank you.
Bye.